We naturally assume that when a massive system collapses, whether we're talking about financial markets, institutional bureaucracies, or engineering networks, it's because someone, somewhere, made a mistake. We inherently look for the error, the flaw, or the irrational choice that brought the whole structure down. But what if the exact opposite is true? What if catastrophic failure isn't born from irrationality at all, but from a rigid, mechanical adherence to it? Let's take a closer look at the hidden structural forces that actually govern our complex environments. There's this deeply held common belief that we all tend to share. We think that perfect data and highly logical decision-making will inherently protect us from collapse. We assume that if every individual component of a system is optimized to operate perfectly, the system as a whole will achieve perfect stability. We treat computational intelligence, endless metrics, and rigorous cost-benefit analyses like they're ultimate shields against chaos. But here is the contradiction we have to confront right off the bat. Perfect, highly rational, localized choices are exactly what trigger global failure. When we zoom in and perfect just a single variable, we aren't actually eliminating risk at all. We're simply moving it. And often, we're moving it somewhere entirely invisible to the decision maker. It's a paradox. We are making better, more calculated micro decisions than ever before, yet our macro systems are becoming increasingly fragile and prone to sudden, irreversible collapse. To see how this actually plays out, let's picture a simple physical system. Imagine a steel beam structure supporting a really heavy load. You notice a slight bend in one of the middle joints, so you rationally decide to reinforce it. You add thicker steel plates, you tighten the bolts, and you completely eliminate that local flexibility. But the kinetic energy of that load doesn't simply vanish. By locking that single joint into perfect, unyielding rigidity, the stress is silently transferred straight down the beam, settling directly into the foundation. You made the joint perfectly safe and the entire structure inherently dangerous. This happens because the system and the agents operating within it literally cannot process everything. Decision makers have finite computational resources. The environment they operate in is infinitely complex, throwing a relentless stream of variables, probabilities, and conflicting data at them. Doing a true, complete cost-benefit analysis, one that calculates the downstream effect of every single action on the entire network, is mathematically and practically impossible. The system is operating under strict, unyielding cognitive and processing limits. So, how does the system survive this crushing cognitive load? It substitutes complexity for simplicity. Entirely under the radar, the system starts dropping variables. When it's faced with a computationally complex target that it cannot possibly measure, it seamlessly swaps it out for a simpler, easily calculated attribute. It evaluates what's readily accessible instead of what's actually true. This is an automatic survival mechanism. The system trades comprehensive accuracy for the immediate ability to just keep moving forward. This constraint is known as bounded rationality. As first identified in the mid-20th century, humans and systems don't naturally seek optimal solutions. They seek satisfactory ones. Because our rationality is strictly bounded by time, mental capacity, and the sheer difficulty of the problem, we act as satisficers. We take whatever incomplete information we have at the moment and make a choice that is merely good enough to relieve the immediate pressure. But as the environment becomes more complex, this good enough approach starts generating friction. Unpredictability rises. And in response, the system desperately attempts to regain absolute control. To manage the uncertainty of bounded rationality, authorities and managers introduce rigid standards. They implement strict targets, precise metrics, and key performance indicators. They essentially attempt to force the system into predictable obedience just by measuring its outputs. Let's return to our physical beam structure for a moment. Imagine a new target has been set. The structure must now carry 20% more weight without showing any visible bending. Pressure is applied. To meet this strict measurement, the local joints are aggressively optimized. More steel, more bolts, maximum rigidity. The sensors at the joints report perfect compliance with the new target. But deep down in the concrete base, completely out of sight of those sensors, a microscopic structural fracture begins to splinter and grow. A really disturbing behavioral shift happens here. As the pressure to meet these new targets intensifies, the actors within the system begin to game the indicator. The actual original goal, maintaining a safe, stable structure, gets entirely abandoned. It's replaced by a singular obsession with satisfying the explicit measurement. The localized rational decision is no longer about the holistic health of the environment. It is solely about ensuring the metric reads correctly, regardless of the hidden costs. The metric stops measuring reality and begins manufacturing a highly optimized artificial illusion. This inevitable collapse of intent is governed by Goodhart's law. Any observed statistical regularity will tend to collapse the second pressure is placed upon it for control purposes. Basically, when a feature of a system is picked as an indicator of that system's health, it inexorably ceases to function as that indicator. People start to manipulate it, the system turns on itself. Before we continue our explainer on systemic failure, I want to briefly pause and mention Sift. Sift is a news app I built. It provides a calmer way to stay informed by highlighting only the most important information, completely skipping the endless headlines and sensationalism that usually demand our attention. If you're interested, there's a link in the description. Now, let's step back into the mechanics of our structure. Returning to our system, we see the structural constraint really tightening. As the environment demands faster, cheaper, and more heavily measured results, the system is forced into harder, increasingly irreversible choices. The easy optimizations have already been made. Now, the system mathematically has to sacrifice vital components just to maintain the illusion of control and satisfy the local targets. To manage this, the system mathematically sheds conflicting criteria. To optimize for speed, it discards resilience. To maximize pure output, it permanently closes off alternative pathways. These discarded variables are conveniently labeled as inefficiencies. The system trims them away, fully believing it's becoming leaner and more rational. It abandons redundancies solely to ensure its immediate survival against the metrics it is being judged by. This is the harsh reality of multiple criteria decision analysis. In complex environments, there is almost never a unique, optimal solution that satisfies all needs. Criteria naturally conflict. When a system explicitly trades off certain criteria, like flexibility and redundancy, in favor of highly measured outputs, it mathematically guarantees the loss of holistic balance. It is making an irreversible trade, swapping long-term systemic health for short-term localized perfection. So we look at our physical system one last time. The local targets have been met perfectly. The final joint is locked. Rigidity is maximized across the entire span of the beam. It's mathematically optimized, highly efficient, and completely unbending. And because it cannot bend to absorb a sudden gust of wind, the unseen fractures in the base shatter completely. The foundation fails. Total, irreversible collapse occurs in an absolute instant. The variables that the system discarded in the name of local efficiency weren't useless waste. They were, in reality, the system's structural integrity. By treating resilience and flexibility as inefficiencies to be optimized away, the system permanently lost its adaptive capacity. It became a brittle shell, perfectly designed to handle yesterday's exact measurements and entirely incapable of surviving today's reality. The overarching realization of why this happens only really emerges through systems thinking. This is the understanding that a system isn't just a collection of isolated parts, but a complex web of interconnected relationships. The failure occurred because the decision-makers treated the system mechanically, splitting it into local parts to be independently perfected. But you absolutely cannot optimize a relationship by hyper-focusing on just one side of it. If we retrace the timeline, we see the irreversible mechanical steps. At T1, cognitive limits were hit and complexity was dropped. At T2, rigid metrics were targeted to regain control. At T3, conflicting alternatives were permanently closed off to satisfy those metrics. And by T4, total lock-in was achieved. The escape route didn't disappear at the moment of collapse. Escape became mathematically impossible the very moment localized optimization began. We are left with a final, chilling realization. Catastrophic systemic failure is rarely an accident. It's not the result of foolishness, or a lack of data, or a sudden mistake. It is the precise, intended, and mathematically inevitable endpoint of perfect local rationality. The system was never failing. It was following its structure.